Hello everyone, I am Ms. Akanksha Gurule. So in the previous lecture of physical chemistry, we have seen the review of thermodynamics in which we have seen the basic points or basic concept that are used in thermodynamics. So in today's lecture, we are also going to study some points and the laws of thermodynamics. So in the today's lecture, we are going to learn what is the reversible and irreversible processes, zeroth law, first law, second law of thermodynamics, Einstein's equation, standard state and standard enthalpy of formation. So now let's begin with our lecture. First, we will study reversible process. It is a kind of process which can be reversed in the same path and without leaving any effect on the system and the surrounding. That means any process which can be reversed having no change in the system and the surrounding. There are some important points that reversible process occurs infinitesimally slow. At each point of the reversible process, driving force is infinitesimally large than the opposing force, so that by slightly increasing the opposing force, the process can be reversed. Next is irreversible process. The process which does not occur infinitesimally slowly, so that the successive step of the direct process cannot be retracted. This means the reverse process is not possible. So these processes, that is the irreversible process, occurs very fastly and rapidly. All natural processes are thermodynamically irreversible. We will take one example, the water flowing from the top of the hill towards the downward. Such natural processes are irreversible processes. Now we will learn laws of thermodynamics. First we will see zeroth law of thermodynamics. If the two thermodynamic systems are each in thermal equilibrium with a third one, then they are in thermal equilibrium with each other. So in the previous lecture we have seen that what is thermal equilibrium? Thermal equilibrium, when the two systems have equal temperature, then that two systems are said to be in thermal equilibrium. So imagine that there is one system A which is in thermal equilibrium with system C, and there is one system B which is also in thermal equilibrium with system C. Then according to the zeroth law of thermodynamics, the system A and system B are also in thermal equilibrium with each other. Now we will see first law of thermodynamics. There are many statements for the first law of thermodynamics. So one by one we will see. So first is it follows the law of conservation of energy. That is, energy can neither be created nor be destroyed and can only be transferred to one form to another. The next is the internal energy U of an isolated system is constant. In the previous lecture we have studied what is isolated system. So isolated system is such a type of system in which neither energy nor mass gets transferred between system and surrounding. So we denote internal energy by the symbol U, and when we write the change in internal energy, it is denoted by delta U. So now delta U total of an isolated system is equal to change in internal energy of system plus change in internal energy of the surrounding. So according to the statement, the internal energy of an isolated system is constant. That means there is no change in the internal energy. So therefore it is equal to 0. So when we transfer this delta U of surrounding term from left hand side to right hand side, we get delta U of system is equal to minus delta U of surrounding. This implies that the amount of heat transferred from the surrounding, that much amount of heat is absorbed by the system. The next one is the internal energy can be changed only if the heat is supplied to the system or if any mechanical work is done on the system or by the system. That means the internal energy of any system can be changed only by two steps or only by two quantities. That is, if the heat is supplied to it or if any mechanical work is done on it. So there is also another form, that is delta U is equal to Q minus W. So what does this plus and minus sign indicates? When there is a plus W, this implies that the work is done on the system by the surrounding. Whereas when there is a minus W, it implies that the work is done by the system on the surrounding. So if the work done is the expansion work, then we know that expansion work, that is W, is given by minus P delta V. So when we put this value of W in the first equation, that is delta U is equal to Q plus W. So instead of writing W, we are writing minus P delta V. Now to predict the heat supplied, that is when we have to find Q, we are transferring this term minus P delta V from RHS to LHS. Then it becomes min plus delta V. That means Q is equal to delta U plus P delta V. If the change is very small, then it can be written as dq is equal to du plus pdv. So always remember that when the change is small, then it is denoted by d, and if the changes are large, it is denoted by delta. So the next is Einstein's equation. So Einstein's in 1905 shown that energy can be created by destruction of the mass, which is given as E is equal to mc square, and it is known as Einstein's equation. This is the most important equation in physics as well as in physical chemistry. So this m denotes the mass of the object and c denotes the velocity of light. So next we are going to see the limitations of first law of thermodynamics. The first law of thermodynamics does not predict the practical observation of flow of heat from the colder to hotter body without external work. So, according to the first law of thermodynamics, heat may on its own flow from an object at higher temperature to one at a lower temperature. This is possible practically. But according to the thermodynamics, heat can also on its own flow from an object at lower temperature to one at higher temperature. Therefore, this is said to be the limitation of first law of thermodynamics, that it cannot predict the practical observation of flow of heat from the colder body to hotter body. The next is the first law of thermodynamics does not prevent us from converting heat entirely into work. According to the first law, we could convert all 100% of the heat available to us into work. And similarly, all the work could be converted into heat. Again, we know that practically this is not possible. So these are the limitations of first law of thermodynamics, which leads to the formulation of another law known as second law of thermodynamics. So according to the second law of thermodynamics, it is impossible to extract some amount of heat from a hot reservoir and use it all to do work. So this is the first condition, that is to extract QH amount of heat from hot reservoir and convert it all into the work. So according to the second law, some amount of heat must be exhausted to the cold reservoir. That means some amount of heat is get exhausted to the cold reservoir. This prohibits the possibility of perfect heat engine. This statement is known as Kelvin-Plank statement. So basically, it is impossible to construct heat engine with 100% efficiency. The next statement is the energy will not flow spontaneously from an object at low temperature to an object at a high temperature. That means if we extract QC amount of heat from the cold reservoir at temperature Tc and convert it all into QH and supply that heat to hot reservoir at TH temperature. So there must be some work to be done to extract QC amount of heat from the cold reservoir and convert some amount of it into QH, that is to supply the heat to hot reservoir, which means that spontaneous flow of heat from an object at cold temperature is not possible. The next is standard state. So in the previous lecture we have seen the state of a system. In that we have studied the state of a system means the condition of the system. So such a condition at which the system is at 1 atmospheric pressure and 298.15 Kelvin temperature is called standard state condition. Next is enthalpy. It is the heat energy that is being absorbed or evolved during the progression of a chemical reaction. Basically, we know that enthalpy is total heat change. Now, standard molar enthalpy. The enthalpy of compound at 1 atmospheric pressure and 298.15 Kelvin temperature is known as standard molar enthalpy. There is one short note that the standard molar enthalpy of pure element is taken as 0. For example, we will take hydrogen. Hydrogen in its pure form is present in gaseous H2 form. Similarly, bromine, it is present in liquid Br2 form, whereas iodine, it is present in a solid I2 form. So the standard molar enthalpy for such element is always taken as 0. So always remember, standard molar enthalpy of a pure element is taken as 0. So the next is heat of formation or enthalpy of formation. The enthalpy of formation of a substance is defined as the heat change that takes place when 1 mole of substance is formed from elements under the given condition of temperature and pressure. That means the amount of heat absorbed or evolved when 1 mole of substance is formed is known as heat of formation or enthalpy of formation, and it is denoted by delta HF. Now we will see standard enthalpy of formation. The heat change accompanied during the formation of 1 mole of the substance in the standard state from its element also in the standard state, that is 298 Kelvin and 1 atmospheric pressure, and it is denoted by delta HF nod. Next is, we will take one example for the standard enthalpy of formation. So here we will see the example of formation of carbon dioxide from carbon and oxygen. So the standard molar enthalpy for the formation of carbon dioxide is minus 393.5 kilojoule. So what is the importance of calculating the standard enthalpy of formation? By knowing the value of standard enthalpy of formation of the various compound, we can calculate the standard enthalpy change for the particular reaction. It can be calculated by delta H naught of reaction is equal to sum of the standard enthalpy of formation of product minus sum of standard enthalpy of formation of reactant. So delta H naught is equal to summation of delta HF naught of products minus summation of delta HF naught of reactant. So for the general reaction, we have taken one general reaction here. The standard molar enthalpy of this reaction can be calculated as delta H naught of reaction. We know that so it is equal to summation of delta HF naught of product minus summation of delta HF naught of reactant. So this small a, small b, small c and small d are known as stoichiometric coefficients. So when we calculate delta H naught of reaction, each and every time we have to multiply each term of delta HF naught by its stoichiometric coefficient. So always remember this formula when we have to calculate the standard molar enthalpy of formation, that we have to multiply each term of standard enthalpy of formation for each compound by its stoichiometric coefficient. So here we have taken the example of combustion of methane. So in this, we know that delta H naught of reaction is equal to summation of delta HF naught of products minus summation of delta HF naught of reactant. Now we are going to put the values. So the stoichiometric coefficient of carbon dioxide is 1. So 1 multiplied by enthalpy of formation of CO2 plus 2 into the stoichiometric coefficient of H2 is 2. 2 into delta HF naught of H2O. So this is a product terms. So now minus reactant. So the stoichiometric coefficient of methane is 1. So 1 multiplied by standard enthalpy of formation of methane plus 2 into standard enthalpy of formation of oxygen. Now putting the values of standard molar enthalpy of formation of CO2, H2O and methane in this equation, and according to that note, we know that the standard molar enthalpy of pure element is always taken as 0. So here we have taken 0. So the heat of combustion or the enthalpy of this reaction is minus 890.2 kilojoules. So the next topic is standard enthalpy of combustion. The amount of heat evolved or absorbed when 1 mole of substance under the standard condition of 298.15 Kelvin and 1 atmospheric pressure is completely burned to form product also in their standard state is called standard enthalpy of combustion, and it is denoted by delta CH naught or delta H naught C or delta H naught of combustion. The same example we have taken, the combustion of methane. When there is a combustion of methane, minus 890.4 kilojoule per mole heat is evolved. So you have been thinking that how the combustion is possible at 298.15 Kelvin, because we know that 298.15 Kelvin means 0 degree Celsius, and how that methane burns. But you have to remember that the above statement does not mean that the combustion is taking place at 298.15 Kelvin. In fact, at this temperature, the combustion of methane cannot happen. This only implies that it is the enthalpy change that occurs when the reactant and product are at 298.15 Kelvin, and during the combustion the temperature is much higher than that. Is it okay? Is that clear to you? So I hope whatever I have taught you in this lecture, you have understood it all. So thank you.